If it works, yes.
I guess so.
You're on.
For private use only. Guess that's the intention. No question. Okay.
Yes.
Good evening. This was an idea from Frank. I wrote a little paper on Java 8 lambdas, and Frank said, "Hey, why don't you come and present this to the JavaSIG?" So I know there's always, as Frank points out, a lot of top-of-the-range guys here that have written books and working on Oracle, and it's quite a few of you whom I know. So you're not going to learn anything on this. Hopefully, so the way I'm going to do this, we've got about 90 minutes, we'll 75, 90 minutes, something like that. So the first sort of 40 minutes, what I'd like to do is give you an introduction to lambdas, and it will seem pretty basic for those of you that have done them before. Quick show of hands, who's used Java 8 already? Okay, so that's good. So the rest of you are going to learn something. So I'm going to try and get you up to speed, because if you jump straight into this, and we go through some code, we've got quite a lot of code demos and things that we can go through, and I'll take a bit of a sort of a feedback from you guys as to which ones you want to go, so we've got lots and lots of code in here. So the first sort of 30, 40 minutes will hopefully get you up to speed. They'll look very basic, we'll be doing some basic things, and it'll allow you to sort of recognize what's happening, and then I'll each slide introduce you to some new bits. Please feel free to ask any questions during the talk. I don't particularly mind if it's during the talk. If they're coming later, I'll just let you know. If not, we'll take questions at the end. And then we've got hours and hours afterwards of live debate where we can sort of talk about ACCA versions in Java and things which I think is quite interesting. There's some other, a lot of this is, I certainly wouldn't claim to be an expert on Java 8 or even lambdas for that matter. A lot of it is, this is one of the books that I highly recommend from Morris Naftalin. These slides are available. I've sent them to Frank. Frank's going to post them, so if you need to take any notes. One of the things I've done is actually in the code examples, there's bits we don't need to go through, but they refer to bits of code, and I've actually put those in the slides, so if later you want to copy and paste, you can copy and paste directly off the slides and put them in the code, so you're coming up with your own implementations. So what I hope, for those of you that do know quite a bit about the Java lambdas, what I hope you get out of this at the end is we've actually used this in practice. It's used with some of our customers. We've got some sort of pretty high performance derivative transaction searching, that sort of thing, and we've been using lambdas in those, and when we get to the code, hopefully you'll see some of the interesting challenges I've had, particularly around splitting streams and things which are sort of supposedly illegal and sort of you're not supposed to do, but they're things that I want to do. So we've been looking for some solutions around that. So, quick overview of some of the features. I don't want to dwell on any of these. The biggest change to the Java 8 language. Who was programming in Java before Java 5 came out, or 1.5? So pretty much most of you. So you'll remember the sort of evolution as we went through Java. It was sort of super exciting, and then we got regular expressions, which, coming from a sort of Unix background, I absolutely loved when those came out. And then we got, again, coming from C, C++ background, we got the templates, sort of generics as they were in Java 1.5, and that was a massive difference. It was a huge difference. And then Java 6, Java 7, nothing super exciting. I mean, yes, there's a lot of work behind it because there was the acquisition of Sun to Oracle. But nothing really super exciting that you would sort of say is going to change things. Java 8, however, is a massive difference. And if we were renumbering these things, Java 5 should have been Java 2.0, this is Java 3.0. There's a huge change to the language in this. And I think people in industries are just recognizing this now, and I've seen a huge acceleration over the last year of other companies suddenly going, oh wow, we need to actually pay attention to this. It's not like, oh, there's just another Java version. Companies are really making a huge effort to actually make their stuff not just Java 8 compliant, because that's very easy to do, because it's obviously backward compatible, but to really put the effort into this. So the language itself is a major change. There's some interesting things done to collections, which you'll really notice as you start to get into the streams, and we'll come back to those. Default methods is a sort of a cross between interfaces and abstract classes. Quite an interesting way of doing it. Security changes. I don't know too much about those. It's really what you get into if you're working on the sort of web front end. I work in investment banking world where physical security tends to be the sort of main way of securing things, so you're physically secure and separated from the outside. JavaFX is a personal favourite of mine, and every time I mention it, people go, "Oh, you don't use that, do you?" But I like it. It is so simple and easy to use, and they've made a huge amount of changes. They've separated the organisation out from the sort of implementation. So you've got the what's it called? The little thing. You can basically, there's a widget. You can say, right, I want this box here, and you can drag and drop things around. And then you've got the implementation, the controllers behind that. So it's very, very easy to use. And I put a couple of slides in here again for those of you that take it afterwards. You can create some really spectacular little graphs and things, animated graphs with literally sort of 50, 60 lines of code. And it makes a huge difference when you go from the command line straight into to be able to produce something that looks visually quite pleasing. Datetime package at last. It's very important, certainly in my industry, with ISO dates, being able to have time zones, all sorts of other bits and pieces. It's a huge change to that, although most people will be using the Joda time for a long time, so it's basically brought that JSR into the Java package. JDBC, for anybody who's still using JDBC, anybody still use databases here? Okay, fair enough. So they put some database stuff in there, for those of you that were still working back in the 2000s. Again, I've sort of lost track personally of the database stuff because most of the clients that I work with tend to be in the NoSQL realms. There are, however, still people that's putting your hands up, still use them, so JDBC with some additional types in there. Concurrency, there's a lot of this is, I think the changes, and some of the experts may well be able to correct me on this, the changes are largely under the hood, certainly with the fork join, which is used by the parallel in streams, which we will be going into, certainly the parallel side, but not the underlying implementation of those. This, however, is not, using parallel is not something that's you should be bringing into your architecture. It's something which speeds up that very small bit of code if you have available processes. Hotspots, these things shouldn't be ignored. When I was working at a bank, BNP Paribas, of course, all of the coders wanted, everyone, I'm sure you'd all rather be choosing to program in Java 8, but we're often held back by the business we're working in. I could name and shame 3 banks that we had to drag screaming and kicking to come out of Java 1.4. When was this? This was last year. These are large banks. One of them happens to own all of your money in this country, so it's a federal bank, so you can get it. So basically, they're using this for a critical part of their business. They don't move it because it works. So they don't need to do further development. It's doing something that they've been doing for 10 plus years. So there's no reason to come out of 1.4. So when we want to suddenly say, okay, finally, guys, we need generics in this stuff. We can't do generics if you're still using Java 1.4. So we had to notify them a year in advance and move them up. But one of the reasons we managed to get the bank to move from one version of Java to the other was not because of all the new features, because they were scared of those new features. They didn't want programmers going off and using everything. And this would be the same very much with Java 8. The last thing you want is programmers experimenting with these things and creating bugs. It was purely because of the performance enhancements. We sold it internally in the bank to go from Java 1.3 to Java 1.4. This is actually when they came out. Purely because of the 20% advantage, and that's saved millions, literally millions, and we're talking not tens of, but somewhere between 10 and $20 million saved purely on the 20% performance increase, just because of the less machines they needed to use, the machines ran cooler, etc., and even going down to the cost of the air conditioning to keep those machines. So the work that's been done in Hotspot should not be ignored. This is something that one of the things that you should be going out and selling into your companies to try and persuade them to move into Java 8. So what are lambdas? Lambdas are functions. You ever wanted to do something really small and simple, but you can't just write a method, it has to be attached to a class. Sometimes you attach it to the class you're currently in, but it's got nothing to do with the class that you're in. And you find yourself putting all these listeners and attaching them. Yes, you can make them static, it's still nothing to do with the class. And what we really want are these, just want this ability to create something that does something really simple without having to attach it to a class of which it's got nothing to do with. So that's effectively what a function is. Often we talk about functions, and then if you're really correcting yourself, it's a method. Java has methods, and you could refer to it as a function, but it's still a method. So this is what a lambda is. It's a pure function. And the clever guys at Oracle have also added quite a lot of cleverness to this. So let's go into an example here where we've got something we want to run in the background. Now, in the slides I've tried to highlight the bits you should be, I'm going to be talking about in red. Sole exception is the next slide, which is in green, but anyway, you'll see how it works. That's the only exception. I've just noticed it because I can see the next slide here. This is a little something you may want to just sort of knock up one day. You're trying to work out, looking at the memory. So all this does is it sets up a little background thread, which every second it prints out the amount of memory we've got, and it prints it out to stand it out, and we can see how much memory we've got. Now, we've had to create a lot of extra stuff here. Yes, you can do without the override, but there's a lot of extra bits. It's just a function. I don't really want to have to create all these little bits. So when we move this into a lambda, it's significantly easier. We don't need to create all of the fluff around it, which is really distracting us from what we're trying to do in this. And with this, we introduce, or Java's introduced this new syntax, which is the arrow, which is basically a dash and a greater than sign. And you'll see that that's been used a lot throughout these slides. This is an empty lambda, there's no variables, hence the brackets, and it's basically saying create a new task. Since task only has one method, the magic is basically that it assumes that this is the bit that goes into that one method. So there's a lot of magic around this that I haven't worked out that's any hard and fast rule as to how it actually works, but it works very, very nicely. So we're going to look at a few more of these. Other interesting ones are listeners. A button, fair enough. You basically have one class. You can have a method on this, and if you want something to do it, you end up actually attaching some functionality of your graphical thing to the controller, because you've now got this my button set on action, and you've actually now got to create a method to do this. You could create an anonymous inner class on that to create an implementation of something, which is another messy way of doing it. And other times you'll have classes where you need to implement 3 or 4 different methods, for example, to handle pick lists, where you've got multiple things. You've got things scrolling off the top, scrolling down to the bottom, and you need to implement an entire class with multiple methods. And again, this is much easier, much better and quicker to do, as you see in the red at the bottom, using a lambda. And basically the entire functionality is handled just in this one part without the extra syntax. Now, for the next few examples, in fact, for quite a few of the slides on here, and actually going into some of the demos, we're going to need to talk about or conceive some data that we're going to be manipulating. So I've created this fictitious data. It's a very, very simple swap. So we're swapping one currency to the other. Now this is a sort of a town, a city where you do a lot of financial services here, as where I come from in London. It's exactly the same, so I'm hoping the vast majority of you will understand the concept here. I did have a version with credit card transactions and bits, but this one I think leads on slightly easier into some of the more complex demos. So we've got a trade ID, which is a long, we've got a trade date. This is the date that it was actually done, buy or sell, so you're either buying something or selling it. Currency 1 and currency 2, those are obviously different, so you're buying one currency against the other, you've got the amounts, and you've got the exchange rate. And a settlement date. The settlement date is typically a little bit later than, it can be the same day, but it's typically a couple of days later than the trade date. So we're going to take this data and we're going to start manipulating, processing it using lambdas. And these will get progressively more and more advanced, and then we'll go into the examples that are still further advanced and look at some of the performance we get out of this. To start with, let's look at the list of currencies. There's a number of different ways we can create streams. We can create streams directly, as we have here, so we're just creating a stream of using a static method. There are quite a lot of interesting static methods. We can actually create streams. One of the easiest ways is to offer collection class. So we can just say list.stream, and we get a stream directly of that. And conversely, as we'll see later, we can go from streams back into collections as well, which is extremely useful. We can use generate, again, we'll see that a little bit later. But this particular one, we now have a stream of currencies. Stream is quite, think of it, if you like a collection, except it doesn't all have to be there at the same time. If you had a collection of 1 million, let's say 10 million trades or 10 million rows, if they're in a collection, they've got to be in memory. If you're using some distributed caching technology, for example, they're still somewhere in memory. Yes, eventually you can stick it on a disk or something, but while we're treating them, they've got to be in memory. The stream, however, doesn't need to be. Yes, it typically is at some point while we're processing it, but the stream, we could be reading the 10 million trades or 10 million bits of data off something else, processing it in the stream, still doing some clever stuff such as aggregation, changing, filtering, etc., and then consuming it elsewhere without ever having to need the entire thing in memory at the same time. And this is quite powerful. It means we potentially need less memory, and we can do a lot of processing more efficiently. You've got less memory, you have less garbage collection, well, same garbage collection, but it's less catastrophic when it kicks in. So we'll start with this currency, and they're sort of, again, more magic here. They're auto-typed. They know their own type, so to speak. There might be an official way of saying this, but I'll use my own magic. It looks like magic to me, so we'll stick with that for the moment. Interesting thing. First thing we'll look at is for each. For each is a bit like going through an iterator, a list iterator. It goes through every single element of the stream. Again, if the stream is something that's not in memory, it will basically consume them from wherever the external source of the stream is and basically print them out. So for each, what we're doing here is we're saying we're creating a variable currency. Now this is worth pointing out. I was always a great fan of, still am a great fan of self-documenting code. So one of the first things I do when someone asks me to sort of look at their code is I basically strip out all the comments. Comments are there, they're normally confusing. They're also cut and paste, and then people change the code and comments made. The thing that's executing is the code, so I like to read the code, not the comments. So self-documenting. So in this case, currency would be the ideal thing to use, but maybe the examples I've looked at, or maybe other people that I've sort of worked with these, I've come to the habit of using one, two or three letters rather than currency, purely because the entire context of what you're doing is often in a very small area, and you've got the context and you don't particularly need the full name of currency. So I quite often just use C for currency, S for string, T for trade, STR, for example, for string, because you've got a lot of stuff that's sitting in an area. If you start to use full variable lengths, it just gets large. So again, for those that are learning lambdas, or this is the first time you've seen them, I'll tend to use a single letter here, but you can use anything you like. Another interesting thing, inside streams, there are some other very interesting implementations which actually allow us to handle primitive types. So there's an in stream, there's a long stream, there's a double stream. These are very powerful if you're doing, for example, how many times have you had to look through an array or a collection of something and find out what the largest value is? How many times have you had to look through and find out what the average or the smallest value of something is? You're looking at something, you want to fit it on the screen, and you want to look at what's the maximum value, what's the minimum value before I actually stick the graph up. And so you find yourself writing this little for loop saying max. If value greater than max, then max equals value, and you're iterating through these things quite annoyingly. So in these in streams, we get some really useful little methods. We can do, for example, like you would with the for next loop, we can just do instream.range 150. The first is inclusive, the second is exclusive, so it doesn't hit the 50. There is another version with another parameter where we can actually make it inclusive as well. But what we get now is the numbers 1 to 49. I'll introduce you here to a filter. And the filter basically is we're working our way downwards here. So we've got numbers 1 to 49. We're calling this little, it is a method in this case, but it could well be a function as well, is prime. And then what we're getting after that is the printout, is the print line. And this is going to give us just a list of all of the prime numbers between 1 and 50. The next one, double stream, the first number, 1, is what we start off with. The second one is what we do every time each time we iterate. So in this particular case, I've created a variable, D for double, again, no matter what we call it. I've said D, the next time I go around, D is equal to D divided by 2. So what this prints out, and another very important thing here is limit. This will go on forever. Well, it'll sort of go on forever until you end up with 0. It'll continue trying to divide 0 by 2, which is still 0, because doubles don't have enough precision. And in a reasonably powerful machine, that'll happen in milliseconds. I haven't tried it, but so what I need to do is limit this. So I put a limit 10. What that does is say, as soon as I reach the 10th element on this, stop. And what happens is it prints out each one of those, and so I get 1, 0.5, 0.25, 0.125, 0.0625, etc. All the way down, I get the first 10 items out of that. And with this, we've got min, max, average. Boxed turns the int into an integer with capital I. It turns double, lowercase d into a capital double. For other usages, we can find out the distinct values. I could put in, for example, a whole bunch of different integers and find out how many of them are, what's the total of the distinct. I could add count on the bottom and count the number of distinct values. You'll find this is very, very performant as well. One thing I use there, which I should point out, is a method reference. This is another way of actually referring to a method. So I could say t arrow system.out.println t, and it's exactly the same functionality as what I put here as system.out, which is the variable, and I'm calling which is the object, and I'm calling print line on that. So this is called a method reference. I don't believe they're any more or less performant, but they have uses, and most of the IDEs now, certainly IntelliJ, if you right-click on most of these things, it'll say you can replace this with a method reference if you want to. So then go backwards and forwards. It's quite useful. So again, looking at the currencies, we can simply say, here's a list of currencies. Rather than the version we had before, looking at the bottom now, we can say system.out print, and out they come. If we miss the n at the end, obviously they'll end up on a big long line. Filters, mentioned before, very, very useful. These could be quite powerful. We'll get on to some more powerful versions of this quite shortly. So looking at the currencies again, we could say filter C for currency. Again, I think it's fairly obvious from the code. We can say filter all of the currencies which are either GBP, British pounds, or euro. And for each of those, print them out. Naturally, we get those two currencies printed out. We could do the same with any currency. We could look for a character inside. So currencies with an A in them, not particularly useful, I agree, but it's just an example to point it out. So let's go back to the data stream that I had. So you've got the common denominator file, and look at how we can start to manipulate that and work a little bit closer. The data will get more and more complex as we go through. So the common denominator file is implemented. We'll create a little class. I think you'll agree it's a sort of pretty much standard implementation for the common denominator file if we want to access it, if we want to work with it. Of course, any of your IDEs will generate all the getters as appropriate to all of these, and even the setters as well. So once we've got the getters now, we can actually refer to these inside our lambdas. It's exactly what we get to do. First of all, though, just again, for those that might use the slides later, just a little bit of code for parsing it. So this code basically parses the common denominator file. I'm sure you can work that out yourselves, but you'll also see some things in here like dateformat.get. In fact, the bit of code that I missed out there is the thread local, because the date format is not thread safe. And if we were putting this into a multi-threaded environment, this would make life a little easier. The other thing here is very primitive. You'll notice if we bung the header into the actual header of the common denominator file, this would die, basically, because it's expecting very specific values. So there's no error checking. It's basically just so you can get your file in. Now we need to, again, not into Java right now, I'm just listing out the code for you. So what we're doing is reading the comment delimited file. We're reading it in this case, into an array list. It's a list implementation. And to get the stream from that, if you look at the very last row, very nice way of doing this, we simply just say the name of the list dot stream, and there's our stream. And this is now a stream of trades. So now when we work with this, we have a stream of trades, and again, it seems to know all about its own type. Sorry, question?
But in that example, you will not get any optimizations in terms of memory. You still get the whole file into...
Oh, absolutely, yes, you're absolutely right. So pointing out here, I'll just repeat the question. In this particular example, there's no optimization of memory because we're having to read the whole file into memory. You're absolutely right. But we've only got 10 lines in this one. As we go further down in the slides, I have a trade generator which can generate 10, 100 million, etc. So, and we won't use the list implementation in that case.
So in this case, can you get the file directly into the stream?
Yes. Yes, I could have done that. I could then use a splitterator, or I could use a generator, and I could read the file line by line into the stream and process it accordingly. Different implementations depending on how I want to treat it. This, again, is purely just code to get people kicked off and started. And also I wanted to point out in this case how we go from a collection to a stream. Because somebody asked, I did this talk for the Credit Suisse guys here this afternoon. One of the questions was whether we can use these stream APIs with sort of existing libraries like a JSON parser or something like that. Of course, anything that returns an array, you can turn into a collection. Anything that is a collection, you can turn into a stream. So the point here was to actually just demonstrate we're going from a collection into a stream. So we've got our stream now. We can print those out, and what we get out is obviously the full list of the trades that we put in the comment delimited file. We want to filter these. Again, not particularly useful filter, but this is trying to make a point, which we'll get in the next slide. This particular one, I want to filter all of the trades where the trade ID is divisible by 3. Naturally, we'll get 3, 6, and 9, as you can see from the bottom. And this is using a very simple lambda. What I want to demonstrate here is the use of a predicate. So if we want to reuse this, we might want to reuse this for some multiple reasons, and we'll get into some of those. We can create what's called a predicate. Now that could have been a method as well, which returns a boolean, true or false, divisible by 3, boolean, true or false. And therefore we could have potentially grouped it in a class which has lots of different filtering functions, for example. In this particular case, we create a single predicate, and we call it divisible by 3. And same syntax, we say t, arrow, t, id, modulus 3 equals 0, so it's divisible by 3. And now we can use that predicate inside the filter, as you'll see in the part of the red. Exactly the same functionality as the one on the previous slide.
Quick question.
Yep.
So the predicate is now a class, right?
It's an interface, I believe.
Class interface?
Yeah.
Is that stored internally as a function or as an object?
Sorry, it's some.
It's no function. There's no function type. They're just reusing.
Yeah. Yeah. So there's no function type. So.
Can that be public? Shared by other classes?
I don't know actually. Can it? One of the Java guys want to answer this and looking around.
It's an interface, right? For
Dozen books. Now, if I wanted to make this public to be reused, my immediate thought would be to make a method out of this, and then make that method public, and have a utilities class that had it. But as a predicate, I would imagine that the predicate could be made public. Does anyone know the answer to that?
You can actually make it a public static final.
Yes.
And then
Yeah,
share.
thank you. So this is just this particular one is in scope. As with any sort of small variable, in this particular case, yeah, thank you. Makes sense. So going back into the currencies, in this one, we've now got the trade stream. We can now actually just say get currency, exactly the same as we did with the strings, and we can say whether they match sterling or euro. What we get out of this, though, the next line down, the for each, the type is still a trade. So when we print these out, we don't just print out the GBP or the EUR, we print out the entire trade. So the type remains the same until we use a map, and we'll get onto a map in a second. So we can also count. This is a sort of a terminator action, so we can actually say, of the trades, how many of them are buy. So we do get the buy sell indicator, we do a match for buy or compare, and we can just do count, and that now returns a long. We can print that out. Again, quite useful. So we're counting how many of these instances, etc. we've got. Maps are very useful. What a map does is it changes the type from one to another. So we can go, for example, we walk through this, we've got the trade list, so we've got the trade stream, sorry. We filter it first by buy, so we get the buys only. We filter it again now by GDP, Great British Pound, and now we do a map. When we do a T arrow, T dot get amount, everything after that magically becomes the type of the get amount, which in this case is a big decimal. So now when we do, if we did a print, system.out print line, we would have a list of big decimals, because that's what we've now mapped it to. So we've gone from trades to big decimals. What I've done here is use a reduce. Now the first element here is what we initialize the reduce with. The next one is what we do every time we come round. So this is like a little bit like iterate. So in this particular case, every time we get a big decimal, we take the sum of it. And if we go back to the data, you'll see the two rows that it picked out, row 3 and 9, have GDP as their buy side, and one Japanese yen, the other one Canadian dollars. Both of the amounts are 7 million, and the result of this is 14 million. And naturally, with certain currencies and things, you could expire the size of long, so I might want to use, this one was big decimal anyway, so we'd be fine with this particular case. But again, if you were mapping into primitive types like ints or longs, you could quite easily exceed the precisions of these types. Another way we could do that is map it to a double. And if we went through this and added up all the doubles, what we're now doing is we're mapping specifically to double. There are lots of utilities like map to double, map to long, map to int, etc. And this particular one, once we've done that, we've got now a stream of doubles, and we can actually do a sum on this. Now, sum doesn't exist for all the different types, so putting sum in there doesn't always work. So you've got to put it into one of these doubles, ints, or longs before you can use sum. The disadvantage with this is, again, as I was saying before, you may lose some precision, because big decimal is always a better choice. It's a really crappy implementation, because it's very, very slow, and creates objects while it's doing stuff, so it's not the ideal thing for high performance, but it works. Sorting. Now, before I can sort, you might have noticed that original one was already sorted, so I'm going to have to shuffle them. So all I've done here is call something that's been around in Java since, I don't know, an awfully long time, probably Java 1.2 or 3. It's just called collections, or it's collections, so it must be 5. So shuffle. And all this does is, as the name suggests, shuffle them up. So now they're shuffled up, I can sort them. Now if I call sort with empty brackets, it sorts by the natural order. Now my trades, I didn't implement comparable in them, so they don't have a natural order. If I had implemented comparable, they would be sorted in whatever I'd implemented. But I can pass a comparator. In this particular case, I've passed, I'm using the comparator class, and using a comparing, which then takes a function, a method reference. So I'm now sorting by ID, and naturally this prints them out back into the original form. Now if I wanted to sort them in reverse order, I can't actually put a minus in front of that, because the method reference won't take that as because it's a method reference and I can't negate it. There is a reverse method, by the way, on comparator, but just for the demonstration of this, if I actually replace the method reference, the get ID, with a t.gets ID, I can actually put a minus in that. So see the one at the very bottom has actually got a minus in front of it. That will sort in reverse order. So these are some things that I've battled with a few times, thinking, how on earth do I do this? And of course you can represent swapping between method references and going back to the sort of lambdas. You find a way eventually. Match all is also quite interesting. If you wanted to apply something to your stream to make sure everything was, for example, valid or compliant or was true, a hypothesis, for example. In this particular case, we look through our stream of trades. What I'm doing is checking that the second amount is equal to the first amount multiplied by the exchange rate, as you would imagine should be the case. And this could obviously be a lot more complicated. You might want to put in commissions and all sorts of other bits and pieces. But what this does now, we simply say match, and this will go through and return true or false. So do all of these match this particular criteria. So one of the other things that you can do with this is we can actually create a predicate out of this, and we can now use the same function as a filter, the same predicate as a filter. And so we now got rate check, which is exactly the same as the one we had before. So we can do the all match as well as using it as a filter. So it becomes quite useful for that. There is a non-match as well, which is effectively negating the logic. So if we do a non-match, we want to make sure that none of these are true in this array. In the stream. So in this particular case, we just want to check that the settlement date is not before the trade date. And as you can see, we do a non-match, date's wrong, again, it's out of Boolean. So we now step up some volume. So answering the question that was asked before, we had 10 lines, and we're not really going to be able to do much significant testing with 10 lines. We certainly can't test any performance or any throughput or anything. So what I've done is I've created a little code generator, trade generator, not particularly complex, and I've put the code into the slides when I come back and use them. So it just generates random currency, make sure that the second currency is not the same as the first one, generates random exchange rates based on a base exchange rate, and then uses a Gaussian distribution of 0.5% standard deviation around that, so we've got a nice little spread, etc., etc. Make sure the trade date is not a weekend, and it creates basically data as you see at the bottom. So I'll skip through these. They're there purely for you to pick up later. Again, a little bit of code generation there. Now, it's a little bit more interesting. We can use this stream.generate. And what stream.generate does is it allows us to put a producer, if you like, inside that. And in this particular case, every time it calls the stream.generate, it produces one of these random trades and passes it back. So out of that, we get trade stream. There are a number of different ways we could have done this. Again, we created this very specific split iterator for it, which we could then define how it's split up and how it's used inside parallel processing. This particular one will sit with the default implementation, and I've now got potentially as many as I want. So if I actually run this and I say tradestream.forEach printout, it will sit there forever. It'll just be printing forever and ever and ever, well, until the machine crashes or someone turns the lights out. And incidentally, we'll get to parallel in a second, if I actually put tradestream parallel in there, it'll actually warm your machine up, because it'll use all of the available threads in there as well, but we'll get to that a little bit later. So we have to introduce limits in this. Again, we looked at it earlier, but if we limit this to 1,000, it's going to generate 1,000 trades. It becomes quite useful. Now, if we wanted to get a list of trades that were just sterling against dollar, if we do tradestream.limit 1,000, and then we say, now filter these by pound sterling and US dollar, first of all, it generates 1,000, and then we get a subset of those. So we'll end up with 23 or so examples. Not ideal. If we swap those around, and we say tradestream, and then filter, and we say limit, effectively we could generate, it would be about 42,000 of these, but we would always get exactly 1,000 of these trades at the bottom. So we can just, by swapping these around, get quite a lot of functionality out of this. However, we don't want 1,000, otherwise it's hardly worth doing it. We want something closer to 1 million, 10 million, or even 100 million. And this is where we can start to demonstrate some of the really more powerful features without having to create lists and collections and various other bits. So we now say a GBP to US dollar trade list, limit 10 million, and run this. Again, I could swap those around and I could actually generate 10 million of these. In this particular case, before someone pointed out, I am actually putting them into a list, so yes, it's going to need a lot of memory to do this. If I swap those around, putting 10 million of these into memory is probably going to tax my laptop quite a bit. So what I get out of this is about, when I ran it, when I was testing it, 238,000. Why? Well, there was 7 currencies in there. The other one has to be different, so 7 times 6, 42. 10 million divided by 42 is the number we get. That's going to vary a little bit, but it's pretty good. We really want to speed this up a little bit further, and by the way, the last one took 18 seconds, so it's generating about half a million a second, roughly. All we need to do is add .parallel to this, and now we can parallelize it. What this does is use the internal splitterator, or the default for this particular implementation, and we'll split it into little chunks and send those off to the available threads. And it creates the same number of threads, I believe, as the number of available processes that I've got on my machine, which is something you can find out quite easily. Again, this is not a solution for creating a multi-threaded environment. This is not an architectural thing. This is not something I would recommend, oh, I can now create everything multi-threaded. This is something that just speeds things up for these few lines of code that you've got on the screen. If you don't have available processes, it's not going to run any faster. If you don't have, all of your other processes are busy, it's not going to run any faster. This is not an architectural change. This is just an optimization that we can put in for this particular case. And if you know you're processing something and you can put in the parallel, and be very careful with this, you know your code is thread safe, because get currency or some of the other things that I'm calling could be non-thread safe. And you'll get some very, very nasty consequences out of that, because when this throws exceptions, it's not quite as easy as you might imagine to actually find out where it went wrong, because I think the compiler or the runtime is not particularly good at associating the errors with the code lines. So it could be interesting. Now, going further still, we can do some other clever things. It's a little bit like filtering, but we can actually start to group things. Now this is very powerful, except that it creates yet another map, or yet another collection at the end of it, which requires lots of memory. Now imagine now you've got some data that you want to process, and I want to process the valid and invalid. So I've got to read it, so I've got to parse it, I've got to do all sorts of bits and pieces. Now I want to validate it, and I want to put all the valid messages here and the invalid messages there. This is perfect for doing that, using a grouping by. So we can say grouping by valid, and it will create us a map of valid, invalid, with a list of all of the trades inside the map. Which is perfect, except it needs a lot of memory to do that. What I was looking for was something that I could actually use as a continuous stream to split them off into two. But keeping to this particular point here, what I've now done is say grouping by currency 1 and currency 2, actually collect, and there's another nice feature using counting, and it allows us to do effectively like a count star for these two currencies. And you can see the output at the bottom. Again, since this is random data, it's very flat. It's always one of the problems when you're trying to generate random trade data or random sort of data. It's always very, very flat. You can see every one of them is sort of 23,000 or so, give or take, and it's very, very unrealistic. We can go further with this still, and we can actually now start to say grouping by, grouping by. We can go much further than that. So now, again, who works in financial services here? Okay, that's an appreciable amount, so please, for those that don't, please excuse these references to financial services, but if in a bank you're trading, you want to work out how much you owe your counterparties, or how much they owe you. It's called reconciliation. So at the end of the day, you take a list of all of the trades and you count up for each counterparty. Counterparty is effectively another bank. You've exchanged lots and lots of money throughout the day, backwards and forwards, buy, sell, buy, sell, buy, sell, and you want to find out of all of these trades, a bit like you reconciling your Visa account or your one of your other accounts, how much do I owe? And so what we're doing here is we're saying from the data that we had before, for all of the Australian dollars, we sold this amount and bought this amount. For all of the Swiss francs, we bought this amount, sold this amount, etc. So this tiny little bit of code here is doing that for us. And that would take quite a bit of work without the lambdas. Now, before we get into the sort of demoing some of the code, that's as far as I'm going to go with the lambdas, because you'll appreciate it gets more and more complex on these bits. I want to go through a few more little bits about debugging and some of the other little issues I've found. I've come across quite a few little issues, and this one is very specific to IntelliJ, and I saw a sort of a good show of hands there. I did this talk at, say, at 4 o'clock to the Credit Suisse guys and said, who uses IntelliJ? And it's like one hand goes up from about 60 people, and all the rest of the 4 people were using Eclipse, but that's what you get working in a bank, I suppose. So in this particular one in IntelliJ, and I believe it's the case in any of the other IDEs, it's some of the errors you get back are not particularly helpful. And things like this have kept me going, annoyed me for half an hour to an hour, or possibly even longer. You think, what the heck is going wrong? Particularly, if I nip back to the previous slide, you got something like this, and things start underlying red, thinking, what's going wrong? And this very, very simple case here, you see these are red, and it says cannot resolve gets currency 1. So what you do, you go back to T, and you click the dot, and then you get a list of all the getters, and it says currency 1, so you click return, and it comes up red, it says cannot resolve currency 1. What on earth is going on here? And it's really, really not helpful. And the thing that's wrong with this is all I did was, if you see the very first declaration there, it says map string, comma, string. That actually should be string, comma, long. So if we go back a couple of slides, it was string, comma, long. So all I did was cut and paste that and change the long to a string. And it hasn't told me that what's being returned is not the same type of a map. It's told me that the currency is wrong. So it's very, very misleading. I found this quite annoying and confusing. Sorry?
Will you compile?
I didn't try. No, it won't compile. No, definitely won't compile.
I had the same experience where it was doing red, but it compiled.
Oh, really?
That's a bug that I
But you're right, it could well be a bug in the IDE. I mean, this one was very simple, but I've had lots of issues like this where you've just got to get, I mean, you go back to this particular one, you've just got to get one of those things slightly wrong, or you've got an extra parameter in there that's slightly wrong, and it just, you sit and stare at it for ages. It is quite confusing. Debugging is another interesting thing. You can't really set breakpoints on these things because they're streams and it just doesn't work. So there's something called peak. I've been very tempted to do quite a lot of stuff in peak, which you shouldn't. It's really just for debugging. So here's a few sort of tips on how to use this. So if we do this particular thing here where we've got an in stream, so 1 to 99, we do peak, and we say print. What we will get here is debug, and then the numbers 1 to 99 all the way down. So debug 1, debug 2, debug 3, etc. That's fine. We do the filter to primes, and then we print them out. So in fact, in this case, we do a count. So we count the number of prime numbers. What happens though if we did 1 to 100 million? Unfortunately, that's going to rather saturate our command line before we actually get the result at the bottom of it. You can't put if and while and for and things inside these lambdas here, so you need to create another predicate. So, or not a predicate, it's a consumer in this case. And because this is an int stream, I create an int consumer. And as you'll see the part in red right in the middle, I've said, this is stuff that I'm pretty sure you all write as I do when I've got large amounts of things. I print out every 10,000th one or every 1,000th one or something like that, just to make sure that things still working and hasn't died, crashed, or stuck in a loop somewhere. And so what I'm doing here is, if n is divisible by 1,000, then I print out. And I'm doing this 10 million times, so I should get 1 million, 2 million, 3 million, 4 million, 5 million, etc. Interesting thing here is, you'll see I've added the word parallel in there. So in fact, what happens is, yes, you get the numbers, but they don't come out in order. So just looking at the bit in blue at the bottom here, those are the numbers that I got on my laptop, because of course different threads are hitting the millions at different times. So I obviously understood why this was happening, but debug without the parallel ideally, and stick the parallel in there afterwards. Now I know we've got some experts here, so I'm going to ask you guys a question. I don't know who you are, so you can probably hide and not answer me. But somebody again in the last presentation asked me if there was a way to optionally turn on the parallel, i.e. to have a parallel, set parallel not, so in such a way that we could turn it on at runtime. Because if we have a non-parallel version and test it and then go for the parallel version, we're changing the code. So does anyone, this is an open question to you, does anyone know a way of programmatically turning the parallel on?
No, we don't have an API for that.
Sorry?
We don't have an API for that. I mean, it's very explicit. You either do a parallel or non-parallel.
It's either parallel or not, yeah, that's pretty much what I thought. I mean, it's an interesting question because I thought it was actually something that would be quite useful. Also sort of limiting the number of threads, yes.
Well, it's a little annoying, but those methods return the same, the string type, so you can do conditional, if you just define a variable for your string, if you want to do parallel, string equals string not parallel.
Yeah, you're right, yeah, you could do two different versions, but again, you're not doing code coverage then, you're not really testing both.
We just, allowing you to test the parallel stuff, we just sort the data at the end.
Right.
So we can test it for that order.
Yeah, that's fair enough. Okay, thanks. It was just a curious question. And again, for completion, I've just put a little prime number thing up there again. You cut and paste, so if you're thinking about it, it took me a few minutes to think about that one. A couple of other little gotchas. You can't. This was one of the very first things that got me and had me say flummoxed because it was very quickly identifiable by a little Google search. You can't use methods that throw exceptions because you can't have exceptions inside your lambdas. I found this extremely annoying. I understand the reasons why, but what you actually have to do is wrap your methods, catch the exception, and then rethrow it, or either throw it away or rethrow it as a runtime exception. It will throw the runtime exception, but you can't have checked exceptions. And it sort of contradicts part of what you're trying to do with the nice part of the lambdas is getting rid of a lot of the crap. Yeah, and then you're actually partly putting it back in just to wrap all these exceptions. One of the things we've done with our code, because we created a code generator, is we've got a little tick box for Java 8, and we actually take away a lot of the useful things like validate, for example. We've got validate, you validate by exception, validate by listener, is to take out the exceptions, parse exceptions, things like that, and then rethrow them as runtime exceptions. It just makes life easier to use them. But it's a little annoyance, something you'll come across very, very quickly. It was literally within a sort of hours of playing with Java 8 that I discovered that, and if you Google it, you'll find it almost instantly. This is the one that's got me at the moment, and it took me quite a while to get to this. Again, it's something which I mentioned at the beginning, is splitting streams. If you're processing a lot of data, we looked at this with the grouping by. If you're processing a lot of data and it's expensive to process that data, for example, you need to parse it. Let's say you've got XML coming in, it's expensive to parse XML, it's expensive to validate it as well. And then once you've parsed it, only once it's parsed can you actually validate it fully. So if you want to put these into two lists, or you want to process these in two different ways, you've got to go through it, either go through it twice, or you've got to store everything in memory. So you're either going to process it once for valid, process it again for invalid, but you're using a lot of processing power to do that a second time. If you can store them, if you have enough memory to store them, that's fine, because you can actually use a map, and you can use a grouping by, and you can say group by sort of valid and invalid, that's fine. But again, we're typically, when we're looking at derivative trades or something, we're looking at multiple tens of gigabytes of data, and you can't put these, you can't really store these things in memory. I've spoken to quite a few of the sort of experts. My colleague Maurice Nathalie has written this book on mastering lambdas, again, which I'll keep plugging for him. And I've found what he agrees to be the least illegal version or way of doing it. which I think only breaks one rule, whereas my first version broke 3 rules. So what I do in this is inside my validation check is I add them to a blocking queue. When I spawn off another background thread that basically picks stuff off that queue. So but what it does mean is I can actually process my my trades at twice the speed, because I don't need to process them twice, and I can do them with a very, very small amount of memory. So I can actually process 25 gigabytes in a Java heap of just 128 megabytes, which is, I think, is quite impressive. If you do that twice, it obviously takes twice as long to do it.
What's the rule that is breaking?
I can't remember. He was the expert. I think it was starting up sort of having sticking stuff onto a separate queue that was outside of the scope of the particular language or what was being called inside the language. Question there.
One question is, let us say if I have a trade that is coming in with 50 or 100 allocations, how will this trading help me in optimizing that process?
So, question about a trade coming in with 50, 100 plus allocations. So you've got a block trade with multiple allocations. Depends how they're coming in. If you wanted to particularly aggregate them, these again would be other challenges. You could map by the block ID and therefore start collecting them under all the allocations under a particular block. They would be held temporarily until they're in the map. If you wanted to stream them without collecting them, then that would be difficult, because the allocations can obviously come in sort of different orders, and at some point you've got to have some sort of, not so much a transaction, but you've got to have a batch at least with all of the allocations. Any other questions? So before we get going to the demo very quickly now, shortly.
Just a quick question. Did you show yet how you limit the size of the stream, how much data it's processing at a time? Instead of like loading the whole file in memory, how you do it in chunks?
No, I haven't got into the splitterators on this. What I was intending, so I was just explaining earlier, the paper I wrote, which I'll link to at the end, which is, I mean, if you've obviously listened to it, well, for those that haven't fallen asleep, the paper, this is based on the paper. So what I intended to do was another version of the paper which assumes you know all of this by now. It goes much more into the details of using splitterators and optimizing performance around that, and how we sort of chunk it, etc. So not in this particular case. There's 3 or 4 more slides I want to go into, and we'll try and look at some code. Let's look at the JavaFX. Now, if you were just looking at numbers, there's no way that you would know by looking at the numbers whether the spread of the exchange rate is Gaussian. It's got a nice Gaussian or normal distribution. And putting stuff on the command line only has a certain, it's a certain limited value. If you're debugging something, or you're looking at stuff, or even if you're presenting it as a prototype that you want to take further, printing stuff on the command line is all very well, but you would be amazed if you've not. Anybody used JavaFX here? Very few of you. You'd be amazed at how much you can do with such little code to get something. That graph is static, but when I run this graph, or if you cut and paste the code that I've put on the next 2 slides, I won't go into detail. That graph animates every second. It redraws itself and animates. It just looks visually appealing. And what it's doing here is basically demonstrating the normal Gaussian distribution of the exchange rate. And you would not be able to see that unless you presented it in a graph. And to change this graph from as it is a bar graph now to a different type of graph is literally 2 or 3 lines of code. So if you can just spend the effort to get into the JavaFX, you can use the lambdas in this. And I'm not going to go through this. This is just literally two pages for you to cut and paste, and that's absolutely everything you need. You need the imports, obviously, but your IDE will help you with that. And that's it. And that basically creates that really nice little graph, which again is animated. So I really, really recommend that you spend the effort just to look at that, because it's no longer like Swing. There's none of that crap that you've got to sort of deal with, and stuff that doesn't work like it should do. This really works nicely. So I'm going to just do a couple of little demos. I just want to show you some of these sort of performance of these things as we go through, just to show you that it's, you've seen the code up there. I'll make all of this code available for you to work with. Bear with me a second, so I'm going to need to share the screen. Any questions while I do this?
Usually people aren't using FX, so you cannot run it in the browser.
Yeah. Yeah, but, yeah.
So what makes the Lambda so much faster? You're just not creating a lot of objects internally? Or just
It's
taking
not
the
that much. It's not that much faster. There's a couple of examples I can. There's one on here, for example, that it shows what I thought was quite a surprising difference between a for loop and a lambda, and then adding the parallel to it. So obviously, if I wanted to do the for loop and make a parallel version of that, it's quite a bit of extra work and code. So for small little bits of code, it's actually it makes quite a big difference. At the end of the day, if you change everything you've got into lambdas, it's not going to make a massive difference to your code. I think what Oracle have put in is a lot of optimization, because of course it knows a lot more. It can understand what your intentions are a lot better from the lambdas than you trying to write multiple for loops and if tests and all sorts of bits and pieces going through. So I was quite surprised by a 15 to 20% performance gain over. There's one line in here which I'll show you. Let me just show you the FX demo actually while it's on the screen at the moment. I mean, that's literally just those 2 lines of page. It's beautifully simple to, if you want to present something, it's nice and simple. It looks nicer on my screen because it's slightly higher resolution. I think there's probably a little bit of pixelization on there, but anyway. Let me kill that. So I've got my got a basic trade. So this is what we had before. So if we go to my object trades, all trade. Oh yeah, sorry, I renamed it for the talk. So here's my trade. So I've got my basic. Enlarge the screen for you. This is what I'm dealing with. It's all the same code that you saw before, and I'm going to. What I'm going to do with this, we'll start with 1 million of them. I'm going to actually use a binary trade, and I'll explain that in a second. When we, this is nothing to do with Java 8. If we create that trade with lots of objects, and we create 1 million of them, there are what, 8 or 9 different objects inside that trade. If we go back to it, that's 8 or 9 million objects. And while we're creating those, it's creating a hell of a lot of objects. So our CPU is spending most of its time creating objects. And then it's also garbage collecting them as well. So that uses up quite a lot of resource. So what I've got is a binary trade. It's not what I was intending to do here, but it just means that the demo runs faster. Rather than sitting here waiting for 60 seconds, I've got a binary version of that, which has the same API, because you see I'm using a factory here, and it just means this will run faster. So I'm going to create these trades here, make it a little bit larger again. So I've got an array size of 1 million. My type that I'm going to use in this particular case, again, this doesn't affect the demo because it's using a factory. I'm going to create the trades, and I'm going to basically create a stream of those, a test stream. I'm going to run a couple of example queries on those. So let me kick it off, and we'll walk through some of what's been drawn to display at the other time. I forgot to change the thing. Let's try this. That's the one. Let's kick that off. So here's my creating trades. It's basically doing exactly what we had before. It's limiting them to a number of trades, and basically what I'm doing is sticking them into a list. So I've now got a list. I've decided these particular ones are immutable. because they're immutable, they have no setters. I've got a whole, I've got mutable, immutable, and various different types of trades. So again, a little bit, demo's a little bit more elaborate than it needs to be for what we were looking at. So when I'm running a query on this, again, let's try and put it on the screen for you so you can see it from the back there. Here's my list. I'm actually doing a timer. I've got my immutable trades. I'm creating, which are in a list. I'm creating a stream of those, and I'm filtering them by the currencies, GBP and US dollar. And then I'm sorting them afterwards, because again, these are now randomly created, so they are naturally unsorted. I'm basically taking the very first one of those, because obviously there's a million of them, so one will do, and I'm printing it out. I do that 3 times because I'm just warming up the JIT compiler on this. And then I'm going to go to serialization test, so let's just look at the results from that. So if we look at the results from that, what this has done is created a million trades. It's sorted them and printed out the top one. It's literally taken 0.2 seconds to do that through a million trades. So reasonable performance on that. And let's look down a little bit further. Run the simple query. Ignore the serialization for that. File, sorry, because I'm working in a small window here. I need to find out the code that I'm looking for.
Control F12.
Sorry?
Control F12 would help.
Yeah, no, sorry. Let's skip to another one, sorry. Excuse me on this one, as I've got the code that I want to show you. Okay, what I'm going to do on this one, I'm going to show you with an interest rate derivative. Well, because we're getting close to time now, so this is a little bit more complex, but this is really jumping into the sort of the really vastly more complex ones. So what I'm doing here is I'm reading, so same stuff, same code, rather than the trades, the single lines, these are real trades. So let me just quickly show you the sort of data that we're processing on these. Go to my resources. This is the XML. This is an interest rate derivative in FPML. It's going to be really fairly complex. If I wanted to search for data in this, this is going to be pretty complex to do. So what I'm doing in this, I'm taking this once. So I parse the XML once, so I'm reading the file in once. I'm going to create a Java version of that, and then my equivalent of the trade generator is basically changing a few details inside this XML. Then I'm going to create an array of 1 million of these, and then I'm going to search through these, and you see this other number here, which is 20. I'm going to search through these 20 million times. So we've got 2 different things here. So what we're going to do is, this should give you a little bit of sort of demo of some of the Java 8 things. So we've got, again, these are the binary streams. So what I've done, because there's no way I would fit 1 million of these trades, each one of these is 25K in size. So if I create 1 million of these, that's 25 gigabytes. My laptop is only 16, so it's not going to work. It will take a long time to do it. However, I do create 1 million of them, but I create 1 million binary versions of these. The binary versions are about 370 bytes. And